Hello everyone, my name is Silvio. I will present this paper named Graph-Based Feature Selection for Intrusion Detection in Cyber-Physical Systems at Perception Layer. The other authors are Professor Diego Passos, Professor Célia Albuquerque, Professor Daniel Mossin, and Professor Luis Oshie. To start, I would like to point out that cyber-physical systems make up our infrastructure of different domains, ranging for healthcare, manufacture, transportation, automotive systems, power, and water industry. And also, it's very important to consider security measures for both prevention and detection threats. And in these recent years, many attacks were reported in the last years targeting power plants, nuclear facilities, airplanes, and electrical vehicles. Therefore, for this reason, intrusion detection systems play a crucial role in cyber-physical system security. Their effectiveness depends on both their detection time and accuracy, because when an attack is occurring, you need to detect it timely and also with a high precision. So feature selection methods can help it to improve the detection accuracy by discarding irrelevant or redundant features. As secondary benefit, reduced feature subsets mean less data to be processed. That means faster processing. So both goals can be achieved by using feature selection, especially the accuracy improvement. That's our focus in this work. So this work investigates how feature selection methods or techniques may improve the accuracy in intrusion detection, especially in cyber-physical systems at the perception layer. In particular, we propose a graph-based meta-heuristic to perform this feature selection, and it runs offline to pre-select important features, and after that use these features to the online phase of our real-time IDS. Our results reveals that our implementation outperforms traditional filter-based approach, as I will show in the next slides. This figure shows a typical cyber-physical system. I will try to be brief here because I believe that most people in this conference already know this concept. But in this figure we can see that there are three main layers. The first one is physical world and the third one is cyber world. And between physical and cyber we have a transmission technology like Bluetooth, Wi-Fi, Zigbee, or any other that connects the data that is collected at the physical world and send it to the cyber world. Similarly, we can have inputs like commands from machine or people at the cyber world that through the transmission layer arrives the perception layer and cause the actuators to perform some action in response to these input commands. And as I told before, our focus here in this work is at the perception layer, specifically at the sensor communication. So in the perception layer there are a lot of attacks that can be launched, and we will focus on three kinds of DOS attacks, three kinds of denial of service attacks. The first one is flooding, and flooding the attackers usually perform it by sending a large number of messages. In our scenario, these messages are advertising cluster head message, a typical message transmitted in sensor networks to sensor nodes become a cluster head. And these messages are sent at a high transmission rate. And the main impact of the attacks can be the energy of each sensor to be exhausted due to processing a lot of messages. The second attack that we will address is black hole attacks, and these attacks is usually performed after an attacker advertises itself as cluster head, and when it becomes a cluster head, it starts to drop all messages received from each node. So the messages that would be delivered to other nodes will be not sent to it, because there are a black hole here that discard all messages. Similarly, the third attack is gray hole. However, gray hole, instead of discarding all messages, this kind of attack is based on a selective discarding, where the attacker has criteria to select which message will be discarded and which one will be not discarded. And this strategy aims at to confuse the IDS, because part of the message are being delivered and part of this are not being delivered. About detection methods, we can classify the IDS into host-based IDS or network IDS, depending on where the features are selected. Host-based IDS consider a single host and collects features from the application level, and network-based IDS relies on network traffic features collected from many hosts. And we can also classify the detection methods based on which approach it uses. There are different approaches such as anomaly-based, specification-based, and signature-based, whereas the anomaly-based IDS focus on behavior deviation from the typical behavior. The specification-based IDS takes into account formal specification like standards to establish which is an expected traffic, and every traffic different from this is considered an attack behavior. And finally, we have the signature-based IDS that uses samples from both normal and attacks to build a model, and from this model perform intrusion detection. So we choose analyze both host and network-based features, and we employ 5 different machine learning algorithms that are classified as signature-based algorithms to perform classification and decide when a sample is an attack or normal activity. So to start with related works, I will talk about GRASP. It's an interactive multi-start meta-heuristic proposed to deal with problems in graph planarization. However, it was been generalized to solve combinatorial problems in other domains. And there are also some works that show that GRASP outperforms traditional algorithms such as sequential forwarding floating selection, SFFS, taboo search, genetic algorithms and mimetic algorithms, and it was also already used to perform feature selection from genetic databases such as waveforms and ionosphere. Also, a few works in literature used GRASP combined with other algorithms such as simulated annealing and IWSS to perform feature subset reduction. All the previously discussed work does not consider intrusion detection systems. There is one work that apply previous approach to detect DOS, probe, R2L, and U2R attacks, but they consider traditional networks. They doesn't consider CPS or WSN networks as we do. In this work, we perform an assessment of a proposed GRASP-based algorithm, which includes of a novel combination of RCL classifiers used for wrapping evaluation and local search procedure. So this technique is combined, build a new implementation of GRASP, and we explore a new domain, that's the CPS Perception Layer. Our GRASP-based feature selection algorithm is composed by 3 main steps. The first one is a grid randomized construction phase. that is represented by the yellow box, and the second one is the local search. This phase is represented by the blue box. So in the construction phase, we will rank all features based on the information gain algorithm. After this ranking, we will select only the top ranked feature to compose a restricted candidate list of features, that is our RCL. So after having an RCL, this step should not be repeated. We will keep this RCL to all grasp iteration. So in each construction phase, we will select part of this RCL in a random way to compose an initial solution. So for example, we will have 5 features as a result of the line 5, and after that we will evaluate this feature subset based on a classifier algorithm, and after that we will perform the blue box algorithm, that is the local search. So in the local search, we will try to improve the solution generated on the grid constructive phase. This improvement is based on small movements such as replacing features from the RCL and the current solution. After a predefined number of iterations on local search phase, we will compute the best local feature subset and compare with the previous generated solution. And for each grasp iteration on the green box, we will save the best feature subset as result. When we achieve the number of iterations, we will output the best feature subset as the output of the grasp algorithm. So in this table, we can see which number represents which feature, and also which are the best feature subsets selected by grasp algorithm in the table 3, and also which are the 5 best features selected by information gain ratio, and on-air filter-based feature selection methods. So in this figure, you can see that for flooding attacks, grasp features outperformed IG, GR, and on-air features except for random tree. For random tree, grasp achieved the same 99.9% of accuracy. For the gray hole attacks, grasp features achieved an accuracy of about 99.9%, except for naive base. However, for all algorithms, grasp features are better than other features. Finally, for black hole attacks, grasp also achieved the best feature subset for all algorithms, and for almost all classifiers, accuracy was above to 99.99%. So as conclusion, at the perception layer of cyber-physical systems and IoT systems, the tiny sensor devices are particularly susceptible to threats due to their limited strength constraints. So it's very important to apply IDS to detect malicious activities. Accordingly, feature selection methods becomes an important approach to enable accurate attack detection. We quantified how a grasp-based feature select implementation can improve the accuracy of 5 classifiers to detect black hole, gray hole, and flood attacks, targeting the CPS Perception Layer. So grasp enabled the classifier to increase the detection up to 31.8% for black hole, 12.26% for gray hole, and 7.7% for flooding attacks. An average about to 17.25 more than with other feature selection techniques. Thank you so much. This is my email, and now I will pass some slide with another reference.